So recall from last time I introduced the Markov chain and the transition matrix.
Oh, we have Gij
denotes the transition probability starting from a location I and moving to j in one step equal to j, right? And the lemma that I left last time was that the summation of Pij j in S, my state space. This summation is always what is always equal to 1. This could be seen, could be explained shortly by just the definition of the P. So we have summation of J in S, Pij. It's just the probability of say x1 is equal to j, given I start from I, and this is just probability of x1 is equal to j, x0 is equal to I divided by the probability of x0 is equal to I. Just the definition of a conditional probability. And we see immediately that by the law of total probability, the J counts for everything inside of the state space, so that the numerator, the sum in the numerator is simply just probability of x not equal to I above x not equal to I. So which is 1, right? So pretty quick. Yeah. All right. So let me move on to the next section, 1.2, on the multi-step transition probability. Okay. So let me take the example from the textbook. That right. So that is example 1.4 on the social mobility. So let me consider this example. Example 1.4 on the social. So what does it say here? So in this example, I denote by xn to be the social class of the nth generation in the family. Right. And the state space here is denoted by the number 1, 2, and 3. Number 1 stands for the what did I say? I want to stick with the so number 1 stands for the lower class. Number 2 is the middle, and number 3 is for the upper class. All right. And the transition matrix is given is given by following. So 1, 2, 3, 1, 2, 3, 0.7, 0.2, 0.1, and 3, 5, 2, 3, 5, 2, and finally I have 2, 4, 4. Okay. So the question that I am interested in for now in this simple model is the following. The question here is, given my parents were the upper, sorry, the middle class, what is the probability that my children are lower class? Right. So that means, suppose I have x naught starting from 2. So I have say 1, 2, and 3 for 3 classes in the society. Suppose I start from right here. So x naught right here at number 2. Okay. Then I want to know what is the probability that at the step number 2, I'm going to land at 1 right here. All right. So it does not ask anything about the middle, about the step number 1, just the step number 2. Okay. That means I could be anywhere. Right. So this is my parents right here. Right. So this is my parents. This is me, and this is my children. Right. So apparently, as you can see, thinking about as a trajectory, in order to go from 2 to 1 in 2 steps, then at the intermediate step, I gotta be somewhere, right? So I gotta be either I go up to number 3, and I'm gonna go down to 1, or I could also do this and go down to 1, stay at 2, and then I lower down to 1, or I would just go down to 1 immediately, and then I will stay at 1. Right. So as you can see in this toy model, there are 3 different paths I could take in order to go from 2 to 1 in 2 steps, right? And basically the way we compute that is just, again, just the law of total probability. Pretty much similarly to this this proof of this lemma right here. So what do I want to compute? So I want to compute probability of what I have x2 is equal to 1 given x naught is equal to 2, right? And so technically, what you really want to do here is, okay, so here I'm trying to go slowly, okay? I'm trying to go slowly for the moment. So what I would do here is I would just use a definition of conditional probability. So x2 is equal to 1, intersecting with x naught is equal to 2, divided by x equal to 2, right? But eventually, if you are more comfortable, you can just skip this step. And then I'm going to do the law of whole probability. That means for x1, I got to be somewhere. So that will be the summation And then I have x1 gotta be, say, let me call it to be a little x, and x0 is equal to 2. Here, the summation here is x is from 1 up to 3, right? So maybe let me say this again. This is law of total probability, just in case, just in case. And of course, I'm gonna divide again by probability of what x naught is equal to 2. Yeah. So then at the numerator, basically, I'm gonna decompose that probability of three steps like this. When decompose again using the conditional probability. So that is summation of probability of x2 is equal to 1, given x1 is little x, x naught is 1, and multiply by probability of x1 is equal to x, and x naught is equal to 1. Everything divided by the x naught is equal to 1. All right. Of course, the x here is running from 1 to 3. And now we're going to invoke the Markov property, namely up here. This quantity right here is just what p of x1. P x1, right? That is a Markov property. The other guy divided by x naught is equal to 1. That is just well, so maybe let me write down here the summation of p x1, right? X from 1 to 3, and then I'm going to multiply by p 1x. Oh, is that 2? So that's one number 2 more. That's 2 here, right? So yeah, I'm sorry for typo. Right. So yes, this is because this fraction, that fraction right there is just probability of x1 is equal to x, given I start from 2, which is simply p2x, right? Denominator. Oh yeah, my bad. Yeah, typo. Yeah, thank you. All right. So what does it look like? So basically, if you look at the matrix, the transition matrix, so I have a 0.7. So maybe let me rewrite 1, 2, 3, or 1, 2, 3. All right. So I have 2x. That means I'm looking at the row number 2. So 0.3, 0.5, and 0.2. I'm going to multiply with this guy, which is basically the column number 1. 1, 2, 3. All right. So this is the column number 1, which is a 0.7, 0.3, and 0.2. All right. So that is just the multiplication between this second row, right, coming from here. So this is basically this is row number 2, right? Yeah, that is a row number 2. I'm going to multiply with the column number 1. So this is the column number 1. Column number 1. So which is right here. Right. So that is basically just the matrix multiplication that I'm sure you have seen this before. Right. So what is so basically, in order to determine the two-step transition matrix, all I have to do here is just to multiply my original transition matrix twice, basically. I just need to square it up. Of course, this is matrix multiplication. So, all right. So, if I denote say P2 to be say the two-step transition matrix, or to say a transition probability, okay, then we have that say P2 of from I to J is simply just a summation of P. So I'm starting from I go to some little x, and then from x I go to J. So x in my state space. In other words, P square two-step is simply just the square of the original transition matrix. Where P is the so to say one step transition matrix, right? Pretty clear. I hope it's not really difficult to see it. And this can be generalized in the following formula, the so-called Chapman-Kolmogorov equation. So we have a, so to summarize the math here, so have a lemma, which is the so-called the Chapman-Kolmogorov equation. So if I denote, so in general, if I denote, say P to the n, all right, to be the n step transition ability, then we have the following. Then we have P of n plus m starting from I to go to j in this number of steps is simply just the well, the summation of Pn from I go to some little x, and then from that x I go to j in the rest of m steps. So x, j, s, right? And the so this, again, this can be seen intuitively by the fact that in order to go, say this is I, right? Say this is j. Okay. So let's say this is n, and this is n plus m. Right. So in order to go from starting from I, and if I want to go to say j in this n plus m steps, then in the middle I gotta be somewhere. So at the time n, I gotta be somewhere in my state space. So either I could go up, go down here, with this, get there, all the way. Okay. And for the proof of this, because it's pretty quiet, I would say not really so difficult, I would just refer to the textbook. But I hope that you guys can already see the reason why we have such a formula. Shouldn't be too difficult. Shouldn't be. Okay. Any question about this? So as a, I should say, as a consequence of this a pretty classical formula is just exactly the formula from the p square we can generalize to any n. So as a consequence, I should have mentioned that for the proof here, just in case. So as a consequence, we have the following theorem, namely, so the n step transition probability is given by so have p n, simply just the original one and multiplied n times. Just n times. So where the original p is just the let's say one step transition matrix. And so from now on, let's say using this formula, for example, back into this example here, I could even ask, say suppose my parents were middle class, what is the probability my grandchildren is a upper class, right? For example, you could ask them, so for which is pretty just just matrix multiplication. So just you only need a calculator to compute. For example, let's go back here. Say that example again. Say the question is, say parents belong to middle, right? And what is the probability? Say my parents probability that my grandchildren, right, say belong to, again, say middle class again. Okay. Yeah, so you could ask such a question. And so grandchildren, that means now I have 3 steps, right? So I have to move 3 steps. So the answer, pretty quick answer is, so I have basically I'm looking for P3 in 3 steps of what? So I start from middle, that was 2, right? So 2 and then stay at 2 in 3 steps. And well, the answer is pretty, so just have to multiply the original matrix 3 times, right? If you multiply 3 times and you evaluate this entry 2, 2, basically. Right. So all you need here is just a calculator, for example. So it shouldn't be too difficult. Yes, please. Uh-huh. The second word, sorry. Uh-huh. Yes, so the entry in the middle, 2, 2. Yeah. Any other question? All right, so that should be it for this short section. All right, so let me move on to the section 1.3, where the math will start to be more interesting from now. 1.3 is what is that? The classification of state. Classification of states. Okay. Before we talk about this section, allow me to fix some notations. Let me introduce some notations from now on. So number one is I'm going to use the P sub x evaluated at an event A is the probability that event A occurs given I start the chain from little x. Okay. The next one is the so I denote by t little y. Denote this to be the first time to say this is the first time starting from one visiting little y. Okay. Where y is a state in the state space. In terms of math, that means I'm looking for this following minimum on the little n starting from 1, such that first time my chain visits the little one. Okay. All right. So the key word over here is at least 1, starting from 1 right here, not 0. Okay, starting from 1. That is the key word. To illustrate what is this, number is the following. Let's say, suppose, okay, so this is time, say time 0. All right, so this is my little y here. Right. Okay. So let's say, so let's say I start from somewhere. I don't know, it could be anywhere. All right. Then I'm gonna run the chain. So say jump to here, jump to there, they jump up to here. But then at some moment of time, I'm gonna hit the little y. So right here. Okay. So the first time I hit y, that number is denoted by ty. So all right. So the first time I hit y, starting from time 0. Okay, so I don't count the 0. I don't count the 0. It will be explained clearer later on, but for now, just remember the definition of this time ty here is the minimum starting from 1. Okay? And so as you can see, this is a random variable, right? This is a random variable because I can never know for sure when I hit y. So this is totally random. Totally random. Okay. And the idea of this will be explained further, but for now, just let me introduce all the necessary notations. And so in general, I can define the k time visiting y. So for, let's say, for a k starting from 2, say, I denote by t k little y to be, quote, k time visiting the little one. In other words, in terms of math, that means I'm looking at the minimum on the n, but now n greater than tk minus 1y, such that xn is equal to little y. All right. So if I hit y the first time, then I'll keep running, and then whenever I hit y again, the second time, that will be my t2y, and so on for t3 and t4, and so on. So for the graph like this, again, so I have the little y there, right? So starting from time 0, jump here, like this. So this is my first time I hit y, right? So then I keep running the chain. And then I'm going to say I hit visit y again the second time. So this is t2y, right? Okay, and then so keep going, right? So I have t3, t4, and so on, and so on. Okay, so again, so this tky here is totally random, right? And I never know for sure the k time I will visit state y. Never know for sure. So it's totally random. And the last notation that I want to fix from now is the probability. And so because this, you can see that these times, they are random, so there could be a chance that ty could take the infinite value. In other words, if I start the chain from 0, there could be a possibility that I never hit y, never hit y. It could be a positive chance. So ty could be infinite. So I'm looking at the following. So I denote by rho little xy. Denote this to be the probability that starting from, I guess it should have, so px and t little y is finite. Okay. In other words, this is the probability. This I will hit y in finite time, given I start the chain from little x. Okay. So note that, so now note that if, let me go back to the greater than 1 over there. If t of little y were defined as, say, t little y is the first time starting from 0, I hit y, all right? Then, what can I say about rho yy? This probability. So yes, it will be trivially 1, right? Trivially 1, and we don't care about that. That's just trivial, and so we don't really include such a situation. So trivial. And that's why I have to emphasize on we start from 1, right? And it's at least 1. Yeah. maybe just let me just write it down more explicitly. So suppose I define this, then the probability I will hit y in finite time, given I start from y, right? Because the ty counting starting from 0. So if I'm already here, I'm already at y at time 0, that means this is always true, right? So given this always true, right? Because ty now is just identically just 0, right? So this is always true. Okay. Yeah. So let me move on to the first rigorous definition, I would say, which could be a little bit confusing at first. So this is the definition on the so-called stopping time. So a random variable, okay, tau, taking value in the natural number, all right, is called a stopping time. Of course, stopping time associated with the Markov chain Xn. If the occurrence of the event, so I should say for all n, the occurrence of the event tau is equal to n, all right, can be determined by the random variable starting from x0, x1 up to xn. Okay. In other words, suppose I give you the directory. If I tell you the directory from x0 up to xn, you can tell me whether this event occurs or not. And that is called tau is called stopping time. Okay. Now, to give an example, let me go back to the ty over here. Let me go back to ty to illustrate the idea. So say number 1, ty is a stopping time. Right. For example, suppose let's say let me say have say I don't know 1, 2, 3, 4, starting from time 0, 1, 2. All right. So maybe 3, 4, and 5. Okay, it's the time. Suppose I give you a directory like this. So suppose I start the chain from 2. In the next step, go up to 3 maybe, back to 2, maybe up to 4, up to say go down to 1. So maybe shouldn't. So maybe go back to 2, and then go back to 4, for example. All right. Suppose I tell you this directory. I want to ask whether the event t of 1 is equal to 5. All right. You look at the graph and you tell me whether that event occurs. Can you tell me that? The first time I won is in 5 steps. Step number 5. Does that occur or not? No, right? You can tell me a definite answer. Definite, remember, the key word here is a definite answer. Okay, so T1 is equal to 5 does not occur yet. Right? So a definite answer. Yeah. See that? If I give you the trajectory of the past up to the current moment, you can tell me whether that event occurs or not. So, all right. For example, let's just say, for the sake of illustration, let's just say do this maybe. Suppose let's say over here, and then go up, for example. All right. Again. So what would you say about this event? The first time I hit 1 in 5 steps, does that occur? No, it does not, right? Because the first time I hit 1 is already at the step number 3 already. So this does not happen, right? Does not occur. So again, so does not. See that? Yeah. Okay. All right. However, if I look at this directory, I could ask you, how about, so T1 is equal to 3, right? If I give you T1 is equal to 3, then I would just forget about whatever later, only focus from 0 up to step number 3. All right. So forget about everything here, forget about them. I don't care. I only concentrate on the trajectory from 0 up to time 3 because they're asking me at the step 3. All right. And then when I give you this path, you can say, okay, so this does occur. Right? Yeah. Okay. So again, so that's why we have a kind of a wording definition. It could be a little bit confusing at first, but basically that is the idea. And so in fact, you can rewrite the ty as an event depending on the xn. So note that we can rewrite the t of y as following. Sorry, to say ty is equal to little n. All right. First time I visit y is at the step n, it can be written as following. Xn is equal to little y. Xn minus 1 is not equal to little y. Other way down. X2 not y, and next one is not y. Yeah, right. You can see immediately that the ty is equal to n can be written as, can be expressed as an event depending on the trajectory from time 0 up to time n, right? Yeah. And so typically this is the way you go. In order to prove something is stopping time, you try and express this event into these, right, into those events, depending on the trajectory, right? And that is how you would prove it rigorously. That is how you could prove it rigorously. So maybe you could go home and try to prove Okay, so maybe a little practice, a little exercise, maybe. Exercise. So prove T2y is a stopping point. Right. In other words, you want to express. In other words, you want to express some T2y is equal to a little n. You want to somehow express something like this, right? So, I should say an event depending on xn minus 1 all the way down to x0, right? Okay. And so on for the T3 and Tk, for example. Okay. Yeah. I already ran out of time, so let me stop here. I will continue on